You guys having a pretty good day? Not sure what to expect from me, right? Me either. I always get to be last, so I never really know what you know or what you don't know. Sometimes it takes a little time to get to know each other. I haven't really gotten in my mind what I'm going to give you as an assignment. I believe you've had exams for the other two sections, correct? I ordinarily don't like giving exams, mostly because I don't think that exams are necessarily indicative of people's capabilities, but there's so many of you, we may have to do that. I think there's something like 30 in here, 25 in here, and another 30 online. But we'll come up with something. So as far as how we're going to evaluate the course, I'll come up with something. I know that's not very reassuring. The last thing I want to do is give an exam, but if that's what happens, then that's what happens. We're going to be in here approximately 12 hours with each other. We'll cover quite a bit of material. Most of it is pre-packaged nicely. The real world isn't so nice. We're not actually going to use software. That's probably a bit of a surprise to most of you, since most well testing and press transient testing and production data analysis is done with software. But the reason we're not going to use software is I want to have a conversation. Once you start to use software, you turn your brain off and you try to get a best fit. Sort of like if I ask you to go through an exercise right now of curve fitting or establishing a model. Let's say I drew y equals x data on the board, and I said, I want you to find the model that best represents that data. What would you do? I bet 90% of you would immediately type the data into Excel, hit trend line, and say, there's your answer. Wrong, wrong, wrong. You need to have a completely different perspective of data analysis for pressure transient and production data type of analyses. And sometimes this causes a problem. It caused a problem recently with some reserves work that I was looking at, where people were using automated analysis schemes and they were getting a curve fit, getting an estimate, and then we were using a diagnostic analysis scheme, and the diagnostic analysis scheme was giving much different results. And they were unhappy with those results because although usually diagnostics gives a lower answer, in this case it was giving a higher answer. And the reason it was giving a higher answer is because the data had not established the model. So on the one hand, somebody is using a blind concept, forcing a model onto something, getting an answer, patting themselves on the back. On the other, we were using data diagnostics to try to tune the model, and the data diagnostics basically were failing, and they were giving an answer which was much different than one would have expected. I don't have these documents mounted on the server yet. I wanted to mention that. I will later this afternoon. Excuse me, my PDF device, I'm pretty, what's the right way to put it, up to date on everything I currently use. It is 12:02, my friend. Yes. Your watch. Very good answer. Ordinarily, I'm pretty up to speed on these kinds of things, but for some reason, the Adobe 10 does not like my computer, so I've been making PDFs with another product that takes 3 days. But anyway, we'll get that straightened out, and we will keep on keeping on. I will have those mounted later on today. It may be late tonight, but I'll send you an email with where those files are located. The videos, they will be mounted on the e-learning site as they have been in the past. I also tend to keep a copy on my site. I think the distance learning people are a bit behind on keeping them on my site, but that's okay. We'll know where the e-learning files are. So that'll be fine. Let me ask you a quick question. Who in here has done pressure transient testing, pressure transient analysis before? Your hands are about this high. Okay. What did you do? Where did you do it? How did you do it?
We started with a lot of exception and running the students, and then we moved on to the
Okay, so this was a course you took in school or
in grad school.
in grad school here? You took Petty 648, and you're taking this because you just want to get to it. Next.
Basically, students don't walk out first. And
In school, another course, not Petty 648.
That is
Okay. How many of you looked at a pressure transient test other than Petty 648? Nobody. And how about production data analysis? Anybody? Okay. So your lines are relatively fertile. I can use that. Now in Petty 648, you say you started with making some sorts of plots and then you worked your way up to software. And you only used one vendor's software? Sapphire, inside Vector. Are there other packages?
this PAN system.
PAN system, Clyde, Weatherford, now UPS. And are there others? There's Propagate software. There's a package they wrote called Welding, which is has a much different learn style and look and feel than Ekron, but actually is probably comparable. Not that I'd want a vendor to know that I'm saying that out loud, but it's a nice package. There's another package called Pi, and Pi is generally used, I think, only by Shell, and maybe a few older users right now. Has a very cliquish clientele. There's a couple of packages for for production data analysis. One is in Akron, it's called Topaz, and the other is in Propagate, it's called RTA. There's now a new version of RTA out called Harmony, which is a monstrosity. It's much more comprehensive and probably in some ways will be the flagship product. But we're not going to use these. Again, remind me why we're not going to use software. Because you're going to turn your brain off and you're going to let the computer do it. I can teach my Chihuahua dog how to use software. I can't teach him how to think about what's going on inside the software. I can only teach him what makes a good match, what may not make a good match, and so on. And then whenever he gets up to present this, what's my Chihuahua dog going to say? Well, this is what the software told me. Not sure that's really going to be a very good day for me. Okay, so in this course, I have alluded to having well test data or pressure transient data analysis and production data analysis, and you can see the different topics we'll cover on these dates. Let me zip back to I've had several requests about whether you have to buy any other text or anything like that, and the answer, of course, is no. The texts that are referenced here are simply as optional reading material. There is a new SPE monograph out, and I apologize, the name of it eludes me. I think it is pressure transient testing, but it's written by Kamal et al. It came out in 2010. It's about as big as a brick. Not sure I'd recommend buying it because it's probably a couple $100, but maybe if you wanted it, you could. Guess we could take a quick look and see. It's nice to be able to spell, right? Yeah, who's got, oh my. Anybody want to read that to me? Thought it was an SP site. Let's try this. No? So the name of the transient well testing. Well, where's the monograph itself? That's not the right one. As you can see, I don't go here very often. About monographs. Am I just going out of my mind, or is it not obvious? Yep, here it is. Okay, so base price is $280. Member price is $140. It came out in 2010, and it's written by arguably the experts in the field. There's also a really good book. I'll throw a copy of it onto the site for you under references, by Kappa. Obviously, it is slanted towards their software. It's called DFA, or maybe they changed the name to something else, flow analysis. It's an excellent resource book, and I will put a copy of that as well. Propagate has a whole bunch of materials on their website, mostly video format. They can also be used. Their videos tend to be very professionally done, very comprehensive, so you could also look at that. Now, of course, you know, when you start looking at things that vendors prepared, the vendor prepared them not for the benefit of humanity, but for the ability to sell software. The last thing we probably need to discuss on the syllabus is that this portion of the course counts a third, and unfortunately some people seem to think that because I am the last guy to do the course that somehow I control the grades. I don't. They give me the grade sheet, I go through and I put my scores in, I average things out. Let's say, for example, you did well in Dr. Harris' part, but you did well in my part. And he said, well, I want an A. Well, don't talk to me, go talk to Dr. Harris, because it's his part of the course. So there, I'll throw that out. Now, the next question probably on your mind is what's going to be expected? Obviously, you've already figured out that I expect you to be on time. It is now 12 minutes past the time to start. Okay, enough of that. I made a little self-study. This is on the website. I can show you the website, and I'm sure the guys will put it on the DL site as well. It's under Petty 663.11b Blasting Game, course notes, and right now it's the only file that's there. It's a self-studying reading file. So if you want to make a quick download of that for your own purposes, you can do that. Later today, the course notes files will be here. Okay, so today what we're going to try to do, I'll do my best, is we'll try to make our way through somewhere around page 70, which is going to be a pretty healthy sprint for us, but the material that I've highlighted in blue includes sort of the basics. I'll rely on those of you who had Petty 648 to keep me honest. if I make a mistake, give me some orientation. But I will have a different opinion, and I will have a different structure of work than you had in Petty 648. Probably should also mention there are other versions of this material, or other versions of this course. I'm sure some of you have already done this. If you go back to the website, you'll see something called Course Archive. Petty 324 is the undergraduate pressure transient testing course, and you can see that I have all the years that I've taught it through there. Petty 324 2009 A was the last time I taught the course as an undergraduate course due to my part-time appointment, but there'll be a lot of information in here. I'm not saying I'm going to take anything from it, but there'll be a lot of information in here. So if you would like to utilize some of that information, you can. There are also versions of Petty 663 dating back to actually 02A, because that was Petty 689 was Petty 663. So you'll see various versions of that as well. All of this is free for your own use. Okay, if we come back, pardon me, to the list here. Are there any obvious things? There's going to be a lot of words today, but are there any obvious things that we've left out? We'll talk a bit about an introduction, then we'll talk about the concepts of porosity, permeability, oil and gas and water properties, and then we'll look at pressure versus time trends. Now, ordinarily, you probably skip the first three objectives because you've already had that. You've had some information from Dr. Ayers on reservoir properties. You probably had some information in your other coursework on estimating oil, gas, and water properties and so on. So that may be something you think you can skip. The introduction is useful. There's a little bit of historical perspective there. But probably in your mind you can skip objectives 1 and 2. We're not going to do that. Good. What do you think is going to happen whenever you have a pressure transient test in a reservoir? What do you think the response is? I mean, think of the reservoir as a human body, and we're going to test it, we're going to stress it. Is there a certain expectation on your part about how things should behave, or how they shouldn't behave? For example, if I were to take your pulse continuously, would I learn that your feet are too big, or you can't see very well, or maybe you're overweight or underweight? What would I learn by taking your pulse continuously? Is there any idea there? What if I took your pulse and your temperature continuously? Would I be able to describe how you sleep, how you eat, how you think? Yeah, so. But I'm not really stressing you, am I? See, we want to cause some sort of a stress in the system in order to get a certain kinds of response. And that's why you keep hearing this word transient, transient, transient. Because fear, for example, is a transient. For some of us, happiness is a transient. We're not happy all the time. We're not afraid all the time. Sometimes other kinds of emotions, they're transient. And we can learn things about ourselves if we have some sort of exposure to these transients. But if we're just doing monitoring for the sake of monitoring, if we have no objective in monitoring, what do we learn? Tough audience. What do you think you learn if you take the pulse and the temperature continuously? Nothing. What if I take your pulse and your temperature whenever I throw you out of an airplane with a parachute? You think your pulse and temperature are going to change? Yeah. What if I take your pulse and temperature the day you get married, the day you have your first kid, the day your wife hits you in the head with a frying pan? I mean, all of these things, they have transient nature. We're going to learn something about each other. Sometimes when you get mad at somebody, you're not mad forever, but your behavior when you're mad determines forever. So pressure transient testing is where we are going to have a controlled stress event in the system. And we're looking at that response, trying to determine reservoir properties. Okay, so philosophically that's pretty easy. The rest of it is about how we're going to perform that event, how we're going to monitor it, how we're going to analyze the results. But to start with, well, let me give an example. How many of you in here like to run? Anybody like to run? I don't like to run. Okay. So what happens if I say, okay, we're going to run 5 kilometers? And you think, well, I'm going to prepare, I'm going to stretch, I'm going to do this, I'm going to do that. And I say, no, I'm going to tie a rope around you, and I'm going to drive my car, and you're going to run 5 kilometers. You know? If you're not properly prepared, what's the outcome going to be? It's not going to be what we hope for sure. And I see a lot of pressure transient tests being run nowadays where people just say, oh, we'll just shut in the well. Or, oh, well, I think we need to put the gauge in first, but I'm not sure. Or, oh, maybe there's something down in the bottom of the well that might affect the pressure transient test or might affect the production monitoring, but we'll worry about that later. So it's sort of like that preparation thing. Sometimes you need to think about that. So we'll start covering this. All right. Here's our objectives, and again, we're going to hopefully get through about number 3 today. By the way, I am not a Microsoft 2010 fanatic, so you'll have to bear with me. Let's see, this looks pretty good to you, right? All right. Is there no way to turn this thing off now? I'll just get it out of the way. Okay, so the objectives of pressure transient testing, we want to evaluate the reservoir pressure. That is the initial or the average reservoir pressure. Why do we need to know the initial reservoir pressure? It doesn't really seem like it's all that important. Why do we need to know it? Sorry?
To know how much you can recover from the reservoir.
Okay, so from a material balance standpoint, it's critical. It represents the initial energy in the system. Coupled with the initial mass, we can determine how it's going to deplete and so on. Do you think people put a lot of effort into that? No. Because when's the best time to estimate the initial reservoir pressure? Hence the word initial at the start. And that means you have to have a gauge down in the bottom of the well. You have to have some sort of a measurement. So people don't really bother with that, especially when they have a lot of wells they're going to drill. Now, exploration wells, that's a whole other story. And offshore wells, that's a whole other story. You'll see a lot of effort put into initial testing. People are trying to get a good estimate of initial reservoir pressure. They're trying to get a good estimate of initial productivity. Why? Because they want to decide whether it's economic or not, whether it's technically feasible to produce. Okay, so using your logic on initial pressure, the same would be true for average reservoir pressure. We want to know something about the average energy of the system so we can estimate it and so on. Okay, what about the reservoir fluids? Why did we need a reservoir fluid sample? When's the last time you really pulled your hair out? Filling out some form or taking a test or something like that? When's the last time you really gave your hair a good pulling? Well, the last time I pulled my hair out was over fluid sampling in a field I was looking at, because all the samples were taken at the surface. But the reservoir fluid is supercritical. It's sitting right on the critical point. If you sneeze on one side, it's a volatile oil. If you sneeze on the other side, it's a gas condensate. But all the fluid samples are measured at the surface. So you really have no idea, what the exact position you are. I'm just making a statement. Also, I remember a study I did when I was not much older than you guys, and we were really struggling to get a handle on initial conditions. And somebody pulled a 40-year-old fluid study out of the well file from Exxon for us. And that really set the basis for some of the work we needed to do, because we were doing some compositional work as well. I just can't overemphasize the need to get a good fluid sample early on in the testing procedure. Now, a lot of people in practice are going to say, well, we might test one well in 10 or one well in 20, or if we really know where we're at, we're not going to do fluid testing. But it's amazing. I've been looking at some data recently where we're tracking liquid gravities. We can also track gas gravities, but it's a little bit more difficult because they don't sample as often. But you can track liquid gravities on a daily basis. You can really see some interesting things happen in the fluids, how they're leaning out, things are happening just almost instantaneously at the time. Estimating the reservoir properties. If you took this course 25 years ago, that's all we would be talking about. We're going to estimate the permeability, the skin factor, the fracture half length, the dual porosity parameters, etc. And that's what pressure transient testing 25 years ago was all about. Making straight line plots, making slopes, making intercepts, getting information about the reservoir, calculating a permeability or permeability thickness product, calculating a skin factor, etc. Then the last one says estimating reservoir volumetrics. Now I want to make sure everybody's reading. I'm going to circle this. Pressure transient testing and reservoir volumetrics. You guys know the phrase oxymorons? Yeah, there's words that don't go together. So pressure transient testing, red keeps disappearing. Pressure transient testing and reservoir volumetrics. Why don't they go together? I'm going to pick on you because you're male. This is a totally sexist experiment. Come here.
Do we have to take all mental off?
No. You just have to turn your brain off, okay? I want you to close your eyes. Close your eyes. I'm not going to hurt you. I'm not going to do anything illegal either. Okay, keep your eyes closed now. Take 4 steps forward. Those aren't steps. All right. Where is he, class? Has he touched the wall? Not yet. He's trying, though. He knows it's there. And that's what the problem is. He knows the wall's there. When's the last time you went running in a dark room? That's exactly what the mathematics are telling us a transient is. Man, this guy's good. He still hasn't. Okay, take 2 more steps.
In front or backward?
Well, you tell me.
I would be safe to go backward.
Yeah. Try it. Step.
Okay.
Okay. So now he knows where the wall is. Okay, so you've hit one of the walls. Have a seat. If you kept going, bouncing around the room until you hit all of the walls, what's that called? That's called pseudo steady state. That means that you found all the boundaries of the system. It's a really weird sort of definition, but a lot of people prefer it to be called boundary dominated flow, whatever it is. But it's not a transient regime. The transient regime is what he was demonstrating with his eyes closed, walking. By the way, what controlled your speed while you were walking? If you were the pressure transient, what would control your speed? The permeability, the porosity, the viscosity, and the total compressibility. But the big one's going to be permeability. They're all going to be related, but all things being equal, the permeability is going to be the kicker. I'll show you something later on today, but I was teaching a short course in Kazakhstan one time, and the chief engineer of this company, pounding his fist on the table, said how much he hated the Kazakh government because they made him test wells. Any of you guys Kazakh? All right, so they make you test the well. But in order to test the well, you have to flare the gas. That's a legal requirement. But when you flare the gas, you get penalized $10,000 a day. So this was like, and I'm making numbers up, but in order to test the well to meet the ministry's requirement, you had to do something that didn't meet the ministry's requirement, so you had to pay a fine. It was some sort of a joke, but that's another story. At any rate, this was a heavy oil mixed with a water that became an emulsion. And the oil, it came out looking like black shaving cream. It was relatively high viscosity, maybe almost 1,000 centipoise at the surface. Probably wasn't quite that in situ, but it was pretty good. At any rate, he went on to calculate, how much they were draining and all this other stuff. I said, that's really interesting. I said, have you ever done a really simple calculation? They were using numerical models. He says, what do you mean? I said, well, just use the drainage radius concept and calculate how far that pressure transient is traveling, because they were doing a 2-week test. 2 weeks. He said, it's 450 meters. Just like that. Stake his children's lives on it, 450 meters. So we ran a calculation, I said, does this look right to you? We did it in class. And he goes, yeah, everything's right. And I said, so let's calculate the number. Do you know what the number was? It was 5 meters. And he pounded his head so hard on the table, it hurt me, And he was banging his fist, and he goes, this can't be right. And so we rechecked everything, rechecked it again, gave some error bars, He was so angry because he finally realized that they weren't testing these wells of any consequence. It was a joke. There was no way that they were getting any representation of the reservoir. It was just a very localized analysis. But we'll talk some more about that. The important thing is to use the phrase reservoir volumetrics in pressure transient testing. If you look at the old books from the 50s and 60s, they always talked about a reservoir limits test. They would produce the well until reservoir boundaries had been felt. How do you feel about that? Good idea? Bad idea? You're going to produce the well until all the reservoir boundaries have been felt. And I'm talking about producing it as a pressure transient test under very controlled conditions. Now, does the reservoir really care? No. It's just a thing. But if you're going to go to all the trouble of carefully monitoring this, every time you hear the word transient, your brain needs to be thinking relatively short term. What's relatively short term? An hour? A week? A month? Now, there are also some issues with how we test wells For example, very tight gas wells, where there's a phenomenon called wellbore storage. We'll talk a bit about that. If you don't use a downhole pressure gauge, it could be months before the pressure at the surface and the pressure downhole come to equilibrium. You heard the words correctly, months. And there was a technology called deconvolution, which was supposed to fix all that. Except that you have to know something about how things downhole and how things at the surface are connected. And you don't know that, so that's pretty much irrelevant. I just want you to realize the contradiction between pressure transient testing and reservoir volumetrics. So if someone says they're going to determine reservoir volume from a pressure transient test, you need to gently raise your hand and ask how that objective is going to be met. If we're in a 50 millidarcy reservoir and we're in 40-acre spacing, that'll take about a month, plus or minus. If we're in a much higher permeability reservoir, it may take less. But that's 50 millidarcies. Now let's make it 50 times 10 to the minus 6 millidarcies. You see my point? There's not enough time in humanity for that to occur. Now, the thing that I like about pressure transient testing is most of the time we're dealing with bottom hole pressure data. And I wrote this down that it's accurate to 1 part in 10,000. But I bought myself some room because I put or more. Some people claim that they can estimate pressures to 1 part in 100,000. Some people claim they can estimate pressures to 1 part in 1 billion. And I keep saying the word estimate, but you can measure it to that level. But suffice it to say that the gauges are pretty sophisticated, assuming you have them in the right place and you always run at least 2, you're probably going to be pretty safe. But again, what happens 3 kilometers down, or maybe even 4 or 5 kilometers down, is completely different than what happens at the surface. So if someone says, I'm not going to waste our money on downhole gauges, I'm going to measure the pressure at the surface and everything's going to be fine, what do you think? I want you have a cell phone right now, I want you to call somebody 3 miles away and ask them what they're doing. Okay, no, you don't really have to do that. All right, now I'm going to give you a piece of string and 2 tin cans, and I'm going to stretch it 3 kilometers, and I want you to tell me if you can understand what somebody's doing 3 kilometers away, because that's the kind of interaction that the surface and the bottom hole have with each other. How much time, how much effort, how much money, how many thousands of man-years have been spent converting surface pressure to bottom hole pressure? And really, how good is it? Okay. There are some certain conditions where it's very good, where we have a single-phase fluid, especially single-phase gas. Sometimes the results are remarkably good. Sometimes when we have a small liquid component, the results are remarkably good. But let's say we produce 2,000 barrels of water a day, and eventually we produce 10 barrels of water a day, and initially we produce virtually no gas, and eventually we produce a few million cubic feet of gas per day. If you don't like standard units, my apologies. Suffice it to say, I'm saying that initially we produce all water, and at some point not too distant in the future, we're producing almost all gas. Your pressure calculation, how's it going to incorporate all that? You're going to have a lot of information in order for that to work, and it's probably going to be non-unique. That answer. So again, you're going to hear me over and over again talking about the value of bottom hole pressure. They always say nothing compares to being there. You guys like, your generation, you like network meetings and that sort of thing? Yeah. But there's nothing that compares to being there. Sort of the same thing with bottom hole pressure. Now the surface flow rate data for pressure transient testing, unfortunately, this can be a problem. Some of you are going to work in large companies and large organizations, and pressure in certain large companies is a relatively cheap commodity. I'll name one as an example. Now Saudi Aramco, all of their new wells have bottom hole pressure measurement. But how do you estimate rate in Saudi Arabia? This is a trick question. Because they don't necessarily. In some cases they do, in some cases they don't. They do what everybody else does. They produce into a battery. They multiply all of the wells going into the battery by some sort of an allocation factor. And they test periodically. This is true in Saudi Arabia, it's true in Deepwater Gulf of Mexico, it's true in West Africa. The surface flow rate data, I just want you to understand that this is a point of great suspicion for me, based on experience. The other day I was looking at a data case of 3 wells in a pad. You'd be surprised to find that they all had exactly the same shape. They were all 3 fingers. They were all going up and down in parallel. Is that a good sign? No. It means that they measured the total and multiplied it by its allocation factor. And that means the rates are wrong. So, oopsie. And by the way, how does this affect our material balance? Pressures are right, rates are wrong, volumes are wrong. This is not going to end well, is it? See, you're taught that everything you get has some sort of truth to it. The rates, beware. Fluid properties, again, we can get those from correlations. Reservoir properties, you can get those from other people, geology or geophysics or the completions people. There may be some error bars on it, but fluid properties and reservoir properties are generally taken to be something that you can get a handle on. Now, you're going to hear a lot of people say, are you talking about net pay or are you talking about gross pay? And this makes me want to pull my hair out because we're always talking about net pay. We're talking about the part that can flow. If the reservoir is interbedded and has 27 layers and only 3 of them can produce, just use the productive capacity of the 3 layers. The results of pressure transient interpretation are the productive capacity of the well, whether or not it's damaged or stimulated, the productive capacity of the reservoir, that's the permeability or the transmissibility, the current average reservoir pressure. And, you know, I put this in black and white, but I want you to understand this is a difficult number to get. This is not something that you walk up to the reservoir and say, hey, what's your average reservoir pressure? Because it's not going to tell you. Reservoir limits testing, this is only true when you're producing the well to pseudo steady state. And probably for most of us in this room, we're not going to see that. Now, I'm talking about producing it as a pressure transient test. We leave production testers on site. We're monitoring everything every half hour or much more frequently in some cases. Pressure we monitor every few seconds. Certain kinds of rate meters we can monitor every few seconds as well. But what I'm really implying here is sort of the protocol that we would use for a pressure transient test we're also using for production. Now, when we start talking about production data analysis, we're going to assume that we have pressures and rates as a function of time, and that we can use those pressures and rates as a function of time to estimate certain things, but that's a completely different mindset. In this case, we're talking about short-term pressure transient testing. So reservoir limits testing really doesn't have a place in here, but you know, for historical purposes, we'll leave it in. What about well interference effects? Have any of you seen well interference effects in the field? I've seen quite a bit of it. I've also seen cases where you know wells are interfering, but you can't see it. from the data. Let me rephrase it. Where you believe wells are interfering, but you can't see it from the data. I've had people go as far as to tell me that even though the signature does not show it, it must be happening. Okay, so even though all the tests say you don't have cancer, you know, my colleague says you have cancer, who are you going to believe? You know, I'm just trying to point this out. Don't take offense to that. But well interference effects are pretty serious business. I mean, because, you know, a lot of people want to see it. Why? Why do people want to see well interference effects? It's like, why do you want to see somebody have cancer? Why do you want to see somebody have something bad happen to them? Why do you want to see well interference effects? One word, well spacing. Well spacing. You want to know what the minimum well spacing is before you have interference. Why? Because wells are expensive. And if you drill more wells than you need, because they're all going to interfere, what's going to happen? That money will be lost. Next is well and reservoir specific parameters. And you see all these different things. C sub S is a wellbore storage coefficient. It is not a reservoir parameter. It is a well parameter. Then you have XF, which is a fracture half length. You have lambda and omega, which are model parameters for a dual porosity system. You have the distance to a fault, L fault. You have the radius for a composite well. You have the KV/KH ratio, the vertical to horizontal permeability ratio. I'll also tell you that despite the fact that you two appear to be completely different human beings, sometimes you can have exactly the same response. So we will have experiences, perhaps, where a dual porosity system, which is a system made up of matrix blocks and fractures, produces a result that looks exactly like a faulted reservoir system, which also produces a result which is exactly like a radiocomposite system. Uh-oh. That means there's three possibilities, which are equally probable, because they all give the same statistics when you turn Ekron on and say, go figure out what the parameters are. The numbers look beautiful. The match looks beautiful. What are you going to do? Talk to the geologists. Very good. Before or after? Always before. You talk to them afterwards, they might tell them. You know? No, I'm joking. But in all seriousness, this one about a fault, I'm dealing with a case right now where somebody believes there's a fault at a certain position. Guys, seismic can't see faults unless they're huge. Okay? And then they start screaming at you, why don't you have the fault 600 feet away from the well? Why is it 300 feet away from the well? Click. Certain things you can see very well from pressure transient tests. Certain things can be interpreted very well, but certain things can't.
Dr. Plaskin,
Yes, sir.
you say there are cases that there's no signature in the production data that show well interference, but you feel that there are. Based on what did you research say?
What we'll look for is a telltale signature in the depletion stem, like on a production data analysis stem, where you're looking at the backside, where depletion has a certain characteristic behavior. It's a 1-to-1 ratio, let's say. If you have interference, then that ratio will be different. It will be, you'll see it on a production decline plot, you'll see it fall below. On a reciprocal production decline plot, you'll see it peel away vertically. In other words, it implies that there's some loss of energy in the system, or some loss of mass in the system. The same thing would be true for water influx or for certain types of pressure support, where you would see an increase in performance relative to depletion. But And I realize those are very subtle features, but I was discussing this the other day with someone who said, you know, it has to be well interference. And all the data are lined up beautifully on a material balance trend. And I said, okay, show me. You know, I'm not saying I'm the expert, you're the novice. I'm saying help me to understand why you think there has to be well interference there. It says there has to be well interference there because if I put a well in between here and, you know, there's interference, then something bad's going to happen to me. I'm thinking, that's not evidence. That's opinion. You know, so we always go back and we look at the diagnostic functions to see if there's any sort of reality to that. Now, I'll tell you also that the problem with using pseudo-steady state or boundary-dominated diagnostics is things that happen like a degrading well condition or something like that, they can show up as a feature that looks like this as well. You have to be really careful about that. You have to know your completion very well. Okay. These are two examples of well test. I'll do a little bit of drawing on here. The base data are the black circles, sorry. These are the base data. This is a so-called pressure drop curve. Now, for almost 60 years, this was sufficient. People looked only at the pressure drop curve. In water resources technology, we were using this in the 20s. I guess we didn't actually start looking at this until the mid-30s. But people were looking at pressure drop only. And then someone came along and they said, well, let's look at some other functions. Now, you guys that have had Petty 648, what would be another function to look at? This is the derivative, delta P prime. And delta P prime is defined as delta T, the time, and then the derivative, d delta P, d delta T, like that. Why do we use that formulation? Why do we use that particular formulation? Why do we multiply the derivative times time? What's your instinct tell you? How many of you classify yourselves as lazy? Okay, I am. How many classify themselves as smart? Okay, I'm not, but how many classify yourselves as dumb? We'll talk about that in a second. But right now, let's talk about being lazy. What we want to do is we want to have a diagnostic function that has the same scale as pressure drop scale. So in order, when we take the derivative, now we have pressure with respect to time. How do we get time out of it? Multiply by time. So delta T multiplied by the standard derivative gives us the units of pressure, or pressure drop. It's very convenient. What's the red curve? The red curve is a ratio of these derivatives. And the reason that I asked who was dumb is because this beta derivative has a unique characteristic that for a power law regime like wellbore storage, it gives us a value of 1, just like you can see here and here. And then it shifts over to a half where it's linear flow. And so this was something we created a few years ago as a diagnostic function to characterize different flow regimes, that sort of thing. So it's more of the data telling you what's going on. So don't worry too much about the beta derivative. It's sort of a puzzle, if you want to think about it, of the derivative function. But that derivative function, who was the father? Those of you who have 648, or the mother, or the inventor, you know? Sorry? Louder. Dr. Economides was the inventor? That's a new one. I haven't heard that one. Okay. Sorry. Greengarden was the inventor? Anybody else? No Hobble English, huh? So, it's amazing how this particular function has so many parents. Because, of course, the flow control people, Greengarden, Bourdais, et al., are credited with this function. Okay. And then I've met people in my travels where I've taught a short course or something, and they've said, I invented the pressure fluid. Know that. Nice to meet you. And then, in some work I did about 10 years ago, I presented a paper on the analysis of late-time pressure buildup data, and I had read some papers by Muscat, and I had read some papers by Russell, and I had done some other work like that. I was pretty proud of myself. And it turns out that Arps and Smith had done exactly the same thing in 1949. They plotted it backwards. They had a little bit different interpretation. They didn't know what a derivative was, blah, 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 but it was kind of a humility moment. And so I would probably credit the derivative as going back to then. Unfortunately, that's not far enough. Because apparently there was somebody back in the late 20s, early 30s that was looking at water resource data, water well data, and they had also developed a similar scheme. So my point is, nobody owns this. This was a function that came into being for certain purposes, and the purpose was to give higher resolution or higher diagnostic value to pressure information. We really couldn't use the pressure derivative until we started having high resolution gauges so that we could pick up these subtle differences. And Bourdais and Greengarden published a relatively simple algorithm for the computation of the derivative, and it's pretty much to the test of time. There are other versions of algorithms that are used for this. I personally prefer this one, that way we can all talk from the same thing. So I would probably recommend the Bourdais-Greengarden type of weight averaging algorithm. Doesn't give the best estimate of the derivative numerically. I mean, if you applied a synthetic case, it might not give you exactly the right answer, but it gives you a consistency because it's a simple weight averaging formula. Now, having said that, what's the derivative used for? Well, if you took a well testing course 30 years ago, the derivative wasn't really in existence, and people weren't using anything again but pressure drop. But then when the pressure drop derivative or the pressure derivative came into being, people began trying to use it to analyze different flow regimes, to see subtleties. In particular, this definition of the derivative for a logarithm has a very unique characteristic. Does anyone remember what that characteristic is? So what I'm about to do is give you your first quiz. So we're going to say that delta P is equal to A plus B natural log of T. Okay, so I'm going to take the derivative d delta P, d delta T. What's that give us? B, and then 1 over, delta T. So when I multiply through both sides by delta T, I get that's equal to B, right? And so what that tells us is that for a regime which has a logarithmic pressure profile, we will have a constant value of this derivative. So interpreting slopes and interpreting, intercepts, that's all really interesting. But when you have a function that's a constant, that's pretty irrefutable. So the pressure derivative came into being more or less because people were trying to identify the infinite acting radial flow regime, because that's a logarithmic regime, and we'll talk about that some more as well. But that infinite acting radial flow regime has a constant value of a derivative, and that was probably what people saw the most value for. You guys ever heard of the pressure integral? I mean, you knew right off the bat about the pressure derivative. You ever heard of the pressure integral? That would be delta Pi is equal to 1 over delta T, integral from 0 to delta T, delta P, d delta T. Something like that. Have you ever heard of the pressure integral? No? I can tell you who invented that. I can tell you where it went. It went nowhere. Every time you think you're a genius, history proves different. I was your age, I was a graduate student. I said, I'm going to use this function to smooth out data bumps and that sort of thing. There were 2 other people that had the same idea and came up with the same sort of concept. I did a lot more development on it, but they were looking at it for something else. But the pressure integral had a short, but like a shooting star, a short-lived application. Turns out it wasn't very fashionable or useful, or wasn't appreciated for pressure transient analysis. But we'll talk about that some other time. So the pressure derivative function is the primary means of identifying flow regimes and analyzing pressure transient data. The pressure drop function is also used. The ratio of the 2 functions, as you see above, the pressure drop divided by the pressure drop, the pressure drop derivative divided by the pressure drop, that's the characteristic beta function shown here and shown up here, and those have a unique characteristic as well. So there might be some value to that. Now this may be the very first set of pressure transient data that most of you have seen. SPE 12777 is actually the Bourdet, Gringarten et al. Paper in the SPE literature. SPE 9975 was a case that our own Dr. Lee presented in a paper 30-something years ago on analysis of low permeability, pressure transient test and low permeability fracture analysis. So both of these were pretty good data sets. They had all the data in the papers. So I put them in sort of a cartoon type of analyses for you, and there's the results. Now, unfortunately, I don't want to go into too much detail, but Bourdet's paper has a trick in it, or has a problem in it, I guess I should say. And the problem is that he shut the well in for twice as long as he produced it, which causes a very interesting effect. Did you guys ever talk about that in 648? No. See, the magic bullet in formation evaluation, pressure transient testing, has always been to get more information from the data than was really there. Deconvolution supposedly could do that for us. But if we had a certain distance in the reservoir that we tested to, and then we shut the well in, do you think that the shut-in sequence can see beyond the production sequence? Yes, no, maybe. Using our experiment. where you took 4 steps. Okay? 1, 2, 3, 4. You set a path in the reservoir. Okay? Now that path is fixed. I shut the well in. What's going to happen? Is the path going to continue to propagate? No. It's going to come up. Now there will be a slight rebalancing out here, but most of the buildup is going to occur at the wellbore. So are you going to see farther into the reservoir during the buildup than you did with the drawdown? No. And so there's this eternal battle, if you want to call it that, about the value of the buildup relative to the drawdown. There was a really, really wonderful paper written by Agarwal, that will never be published, I'm sorry to say, and it was on a function called effective time. What Agarwal did is he figured out how to make buildups think they're drawdowns from the standpoint of how you project the data on a graph. Agarwal. It's used in all the software, by the way. And it wasn't particularly clever, you know, because we had been doing superposition for years. In fact, for tens of years, or maybe 20s of years, we've been doing superposition on well test data. But what he did is said, hey, look, you know, what we did wrong was we formulated the problem in this way. He said, let's shift the problem and look at it this way. And that was the genius of it. Very simple concept. But what it did was it allowed us to look at pressure buildup data on a pressure drawdown basis. Very clever. Because if you didn't do that, you would have an infinite combination of possibilities for pressure buildup and pressure drawdown data. I don't want to restore the writing. Okay. These are static data for pressure transient analysis. Again, these are just things that you're going to need. I'll illuminate you quickly. Those of you who've taken 648, have you used Sapphire nonlinear? Yes, no, maybe. Sapphire nonlinear, accurate nonlinear? No. Why? Because that's just a simulator. And what happens is, whenever you see Ekman standard or Topaz standard or Sapphire standard, that's using constant properties. Not for gas, but for gas they use pressure-dependent properties. But if you're going to start putting in compositional changes, well, permeability changes, saturation changes, and so forth, you have a completely different model. You can't tell that. But you click that, it brings up the completely different model, and you run it. But for right now, we're going to talk about very simplified analyses. You're going to assume constant properties for a black oil. You can have pressure-dependent properties for a gas, and you should, in fact, do that. One of the things that frustrates me about Sapphire and the other well testing packages, they always give you a button to turn off and on the pseudo pressure and pseudo time function. And you probably should never turn those off. I understand why they do it, because when you use pseudo time, it's inconsistent with the drawdown, because the drawdown doesn't use pseudo time. And we can talk about that some other time, but the reason the drawdown doesn't use pseudo time is you have to have a basis in pressure to calculate the pseudo time, and you don't. Now the way you can get around it is you just switch over to numerical and model the whole thing that way. But my point being about, you know, dry gas or using pseudo time or not using pseudo time is just be consistent. Think about what you're doing and watch carefully. Olivier Houzé, who's the managing director of CAPA, once wrote a paper called "We Don't Need Pseudo Time Anymore," "We Don't Need Pseudo Pressure Anymore." And what he was proposing is just to do everything numerical from now on. Why not? Why don't we just do everything numerical from now on? Why not just throw away the course and do everything numerical? Numerical takes time. You're on the right track, but how do you start the numerical? You have to have a whole system of properties. So really, the better way he does this is to do an analytic analysis first. Use that to calibrate the numerical analysis. And of course, that's exactly what they recommend. But his point is that we reached a time where we don't really need to do analytics anymore. But as a teacher, as a practitioner, as somebody who's been a participant in the development of a lot of these tools, I always want to use diagnostics. I mean, okay, somebody in this room will prove something that I did was wrong. I'm sure at some point. That's inevitable. Everybody has classic work that they think they did. Somebody comes along and proves it's wrong. Fine, I'm happy. Every now and then I get screamed at because the pseudo type function I derive for production data analysis doesn't include this. I don't care. It worked for what I was trying to do. Somebody will prove something's wrong. But until then, the diagnostics that we have are the only way we have of calibrating these things. And in fact, the diagnostics probably will live long past everything else we've done. Volatile oil and gas condensate, these are tricky. And you'll notice that the vendor's CAPA in particular has very carefully inserted a compositional algorithm for their fluid properties. Now, how they use that is another story. But the fact that they see they need a volatile oil and a gas condensate algorithm tells you they know this is coming. Now, the reason that volatile oils and gas condensates are so frustrating for me right now is because the last few years I've focused on shales. And certain shales, Niobrara, Eagleford, Bakken, etc., they're all very, very critically, they're sitting right on the critical point. Now, some of the other shales, they could care less. Something like the Haynesville, it's been cooked at, I'm sorry if my centigrade scale's not right, but at 350 plus Fahrenheit, for a long time, so it's basically just got gas. Fayetteville, other shales like that, some of the lower productivity shales. Onondaga, Albany, those shales are pretty much liquids poor, the Marcellus is liquids poor, although there is a portion of it which is not. My point is that there are a lot of sort of systems that are sitting out here on the critical point that we need to be able to go back. Usually use an acrobat, sorry. Just a suggestion. Other reservoir properties, you just had a course with Dr. Schechter, so you should be able to get porosity, you should be able to get thickness, you should be able to get wellbore radius, bit diameter. Wellbore radius is pretty trivial. Formation compressibility, ordinarily, I know I shouldn't tell you this first day of class, but I'll just assume a constant value, or even make it. You can't make it 0, but make it some really small number. The well completion history, the drilling records are something always good to have. I know you live in a generation where everything's electronic, but the reality is a lot of this stuff is not electronic, and you're going to have to get into files, both drilling records and well files. There'll be information that will shock you. If you're involved in any kind of documentation for your company, please, please, please make sure that every comment, every piece of information is somehow stored electronically. It will save you enormous amounts of time and difficulty later on. I was working on a project once where the productivity of this well just went like that. No evidence of anything. Nothing. I mean, not the guy went on vacation, or his wife was pregnant, or the company went bankrupt, just like that. Anybody want to guess what it was? I mean, it's stupid because you never get it, but there was hydrates in the line, and fortunately somebody marked it and mentioned it. That I mean, not very much, but mentioned that they had a problem with hydrates and treated it. And then they had to work on the compressor, and then they had to do this and that. None of this stuff has anything to do with the reservoir. You know, so you're sitting here looking at this, and you're going, oh God, you know, the well's collapsed or something. And if you go look at the annotated records, which were very well documented, you're like, thank God it wasn't the reservoir. Of course, meanwhile, while they had shut it in for all of this work, these wells produce a lot of water, and be picked off, and everything else. Like I said, be careful not to hit the compressor with the water, etc. So just be aware that completion history, you know, the old adage about something, you always find something somewhere, the last place you look. Well, the completion history is probably going to be the last place you look. Production histories, again, this is talking about how we would do this in general. In mature producing environments like Texas, you have allocated rates. Right now in Louisiana, there's a lot of things that are allocated as well on a lease basis. In Pennsylvania, the production records are confidential. In Indiana, they're absolutely unreported, which is really strange. They're common in a lot of offshore environments, and in that case, you'll be looking at manifold rates. The same thing would be true in places like Saudi Arabia. The allocation is going to depend on the records and sort of on how often they do this, so be really careful with that. Pressure data, I don't know, I've probably become more forgiving about pressure data than I have about production data because you feel sorry for it. But you know, like I'm saying, that virtually all production measurements are taken at the surface. In the U.S., I'd say not virtually all, but all production pressure measurements are taken at the surface. There'll be a lot of downhole gauge data in the Gulf of Mexico and the North Sea, West Africa, and so on. Who's looking at that data? Nobody. It's just being written on a hard drive somewhere or written into a file somewhere. Why do they take that data offshore? How much does a well cost, deepwater Gulf of Mexico? I mean, not the $40 billion Macondo well, but how much does an ordinary garden variety deepwater well cost in Gulf of Mexico? 100 million would be a good starting point. The other day I was looking at a workover of a well that had some producing problems. It was $69 million for a workover. I could do a lot with that. If they want to give it to me, I could do a lot. But a workover in deepwater Gulf of Mexico was $69 million. Completion changes are not often reflected in the surface pressure. That'll drive you crazy. Some pressure data are just wrong. I could tell you a story about a consulting job I did several years ago where I went into the manager and I said something's wrong with his data. And he says, no, those data are fine. Next day, something's wrong with his data. No, those data. This went on for 2 weeks. He said, I've called the field. I've found the problem. I said, okay, what's the problem? He said, those data were measured at the manifold several kilometers away, not at the wellhead. You know, as though this were some sort of judgment. I told you that the first day. And you know, there are moments in your life where you realize just how significant you are. No matter how many students you've had, no matter how many papers you've written, no matter how much your kids love you, he looks at me and says, boy, he says, you are the consultant, you fix it. And I said, you want me to take incorrect information and come up with an answer that you have in your head as to this issue? I said, you are the consultant, you fix it. So sometimes you have the professor card, and sometimes you don't. All right. well completion issues, equipment changes, poor practices, failed equipment. That happens a lot more than you think. The unreported activities, again, that goes back to the well completion history. Make sure that, I've looked at probably dozens, if not hundreds, of production data analysis cases where there was a recompletion, but nobody told you, and all of a sudden production gets a lot better, and you're trying to figure out what the hell happened, and you go back and you say, there must have been a recompletion of the work over here, and they go, we don't show that in the records. That's right up there with you or the consultant, you fix it, so that's fine. Permanent downhole measurements, I think the expense is justified. Unfortunately, it is expensive. I cannot think of any downhole pressure measurement installation that's going to be less than 60 or 70,000 US dollars, no matter where. That's for a single point. Continuous. In the whole scheme of things, that's not a lot of money, but it's a lot of money when it's on the well completion guy's docket. When they see that, they're thinking, this is going to hurt, so get rid of it. It will provide a continuous evaluation, and the downhole sampling is not an issue. You can load as many data points as you want. In the last couple of years, I've probably seen downhole data gauges with 30 million data points. So, stuff like that. Pretty common now. Questions about any of this?
Why allocate rate data?
Sorry?
Allocate the rate data.
Why is it allocated?
Don't they measure the production data to each well, one to one?
Every now and then. Every now and then. And they create a factor, and they multiply the factor by the total, and they assign the rate. So let's say that all of you work for me, and I don't get a timesheet from you, but every 2 weeks I test her, and 2 weeks later I test you, 2 weeks later I test you. And so all of your entry-level employees, I'm going to pay you the same, except by the allocation factor. It's completely unfair. It's completely inaccurate. But putting a meter on every well is not going to happen. Not for liquids. For gas, yeah. I would argue probably 99% of gas wells are separately metered, individually metered. The problem with the liquid metering seems to be the threshold of buying the turbine meter and what happens when it goes out of calibration, and also the water leg. Because a lot of these wells will produce a lot of water, and where are you going to measure? They could go, me and you sitting here thinking about this, we could probably design something that would work, but they're not going to want a separator on every well. And I'm trying to think of how, a water knockout, I can see that, but a water oil separator, maybe. But I will tell you, people are starting to realize that metering the oil separately is important, so that we can reverse into what the total was. I think the pushback is always going to be on water. Nobody really seems to care. That part I don't know how to explain. But I will say that certain entities will put a separator on the well, on individual wells, as long as you want, but you better justify it. There better be a reason that you want to do that. And they're not going to do it for 300 wells. They might do it for 30 wells. But the threshold for me is, okay, that's fine. I can probably talk them into that because they understand it. It's at the surface. But why can't I get anybody to do this, to do downhole pressure measurements? It's just that line item cost. Have you ever gotten an estimate for something that you just say to yourself, I could do this, but I don't really need it? If you're going to look to buy a car and you look at the Ford Focus and the Rolls Royce, and if you squint your eyes from 300 yards away, they look the same, you know. So, you know, why not buy a Rolls Royce? You don't really need it. Okay, this is a case history of, okay, I'll be honest, this is my second load. Sometime later I'll show you my first load. But this is a case that we worked on for a number of years. There's only about a year's worth of data here, but we got an update for it. It's a very clever case history. This is a tight gas sand. This company was spending a lot of money on evaluation. This fellow who came up with this idea of testing this well was garden variety, really good classical reservoir engineer. And what the company was doing was they were trying to use production data to analyze these wells and determine how they wanted to do a spacing study or how they wanted to do developmental practices and so on and so forth. So the red are on the left-hand axis here, and the blue, sorry, are on the right-hand axis there, and it's computed flowing bottom hole pressure, and it's measured gas rate. There wasn't a lot of water, so this turned out to be pretty well. You see there are a few shut-ins occasionally. This is long-term production monitoring, so this is like if I was taking your pulse and temperature. So this guy, he decided that he wanted to go to management and get them to run a pressure transient test. And he went to the reservoir engineering manager and he said, I want to run a pressure transient test. And what did the reservoir engineering manager say? He said, get out of my office. He said, it's going to cost me money. I'm going to lose production. This is an 11-day pressure buildup test or 12-day pressure buildup test. He said, it's going to look bad for me. It's going to look bad for you. We're going to lose that production. We're never going to see it again. I said, no, get out of my office. But you can see there they did a pressure transient test. How did that happen? He walked over to the production manager's office. He said, we've got a problem with this well. You better run a pressure transient test. And the production, what? Are you kidding me? Is there something wrong? There it is. He convinced the production manager to shut in the well for 2 weeks and take a pressure transient test. And the beauty of this is, it's true. You know? Now, why he didn't get fired, I don't know, but it's true. So what you're looking at is the measured well test data in green, and then the calculated bottom hole pressure data in blue. I don't think you're ever going to see as close a comparison of computed and computed bottom hole pressure and measured bottom hole pressure as you're going to see here. I know it looks a little bit different. I didn't try to shift it or calibrate it or anything like that. I just ran the computation. How many points are there in green? Well, it looks like there's 10 or 11 points in blue. How many points are there in green? There's about 10,000. So they ran this pressure gauge continuously. Be nice, just FYI, for those of you who really are into this, if they would have run the pressure transient or run the pressure gauge down a few days early, then picked up some flowing bottom hole pressure so we could have calibrated off of that, but they didn't. A lot of people don't do that, but that's okay. So I guess before I switch slides, let me explain to you what I'm thinking here. We've got an interesting case of rates. The rates are probably pretty good. They're metered at the well. We've got a pretty good case for bottom hole pressure. It was relatively constant, but and the surface pressure was as well. But we computed a bottom hole pressure. It shows the shut-ins. It definitely captures the big shut-in. And the measured pressure transient data that you see in green, they agree pretty well. So the question is, what are we going to do? And we're going to do pressure transient analysis, and we're going to do production data analysis. Now this is the pressure transient analysis for this well. The red line is the 10,000 data points. So the red and the green, there's 10,000 data points. And then the symbols, you can see I've superimposed the pressures that occurred during that shut-in on top of this. Of course, I'll use sapphire to do this. What does it tell you? Now, how many of you had 648? Raise your hand. Touch the sky. All right, so 6 or 8 of you. Can you get a better match than that? Can you match the red and the black better than I did? Sure you can. Come on. I never met somebody who didn't think that they were an ace on pressure transient testing. Anytime you ask somebody, can you do pressure transient testing? I say, I'm good. I can do a great job. So how come I didn't do a better job? Do you have any sayings in China about old people?
Yeah, we always say that older people are smarter.
Yeah. We say that age and treachery defeats youth and energy. So remember, that's always my tactic, is age and treachery, okay? So I'm being treacherous. I'm being deceitful. I'm not telling you the whole story. Okay, so the black line and the red and the green lines, they match up okay. Not great, but okay. We'll come back to that later on. I just want you to think about it. Anybody know the answer? The reason I flashed forward is I couldn't remember if I included the discussion. I did. The black line is not from pressure transient analysis. The black line is from production data analysis. So I did not analyze these pressure transient data. I analyzed the production data, and then I superimposed the model on the pressure transient data. So this is a blind test of how well the pressure transient data and the production data analysis work. So in that regard, it's pretty good. In that regard, it's fantastic. We'll talk about that some more. All right. So this is a 1935 monograph on back pressure testing of gas wells. How many of you imagine one day writing a book? Anybody? You gotta have some ambition. Nobody wants to write a book. So this book has exactly one equation of any technical consequence you're looking at. That's the equation. Now there was some other stuff about metering and other things, and there's some metering equations in there. But this book is devoted, like a parent is devoted to their children, to this equation. Where'd this come from? Now, what's completely empirical mean? How did they come up with this equation? Nobody's going to say? So they made a log of P bar squared minus PWF squared plot versus log of rate, and it did that. Well, jeez. Let go. There's your equation. This is the basis. This is the primordial ooze from which pressure transient data, and actually all modern reservoir engineering came from. And it had nothing to do with estimating reservoir properties. It was about quantifying the well potential. Why? Why did anybody care about quantifying the well potential? And you realize this book was written in 1935. So that meant that the stuff that went into it was probably 10 years old, like all books. So this is probably the 1920s technology represented here. Why did they want to know what the maximum well potential was? What did your parents really want you to do? They didn't want you to do what you wanted. What did they want you to do? A doctor. What about you? What did you do? Doctor. Engineer. Holy cow. If I was playing poker, I'd have a raw flush here. I got 3 of a kind on each hand. How about yourself? What did your parents want you to do? And? Engineer? Pilot? That's sort of a joker card. Next. A lawyer. I was waiting for you. Sorry? A faculty member? That's not low English. Sorry? As a politician. Okay, so we got a lawyer in the group, right? So you're a lawyer. You don't know anything about technology. You know that one number is bigger than another. You know that golf is from 2 to 4. You know that you got to bill lunch so somebody else can pay for it. You got all this. What do the doctors know? Nothing. They're doctors. Focus. Right? But you have to be fair. So all of us in this room, except for you, have an interest in oil. We're all producing wells. When we come to you, we say, we need you to figure out a fair way to tell us to produce our wells. Why? Because she's producing her well as maximum. He's producing his well not at maximum. He's losing revenue. So I'm coming to you. You're not just a lawyer, you're a politician. So it's like a double negative. So now, you have to figure out a solution. What are you going to do? Anybody? So what you did is you said, okay, we've got this equation that describes the performance of a well. We've got a testing procedure, 4 points. And we're going to construct this plot. We're going to get this estimate of the maximum flow rate of this plot. And everybody in the room has to do this. And then you're going to sit down and you're going to decide how much of my maximum I can produce, how much of her maximum she can produce. Because that's the only fair way to do it. You know where that was invented? It was invented in Austin. about 100 years ago. Exactly like I just described. The Texas Railroad Commission. Why does the Railroad Commission have control of the oil and gas industry in Texas? Because the government assigned the oil and gas sector to the Railroad Commission. It's that simple. Okay? So what we would do is we would come over here and we would estimate the maximum rate. So we would say at 0 PWF, this is our maximum rate. We're going to call it AOF. Okay, so the absolute open flow at PWF equals 0. And each of us get one of these. And how often do we have to do this? Mr. Lawyer / politician? We have to do it once a year. Okay? We have to test our wells once a year. Is that still true in Texas? Yes, it is. Except that now, you can see we need 4 points to describe a line, right? But how many points do we really need to describe a line? 2. Not in Texas. You only need 1. So now, you can do a single point test and draw a line through there because the slope is going to be 1. That's what we're assuming. And because that will give you a lower productivity, and you can make your AOF from that. So from this political / legal requirement evolved what? Reservoir engineering, as we know, because this isn't sufficient. But it's a simple answer to a very complicated problem. Land ownership is a complicated problem. How do you keep a landowner happy? What's the minimum distance you can have a well from a fence line in Texas? And I know you're thinking, why are you so obsessed with Texas? I'm just trying to explain Texas because the world mimics Texas, okay? All right, so what's the minimum distance? It's 330 feet. You can get a waiver, but you're going to have to be nice, especially to your neighbor. So there's still things that are in effect even now, 100+ years later. Now in a country or an entity where all the minerals are owned by the government, this may seem to be irrelevant. But a lot of countries have copied this concept. Why? Was it because most of the oil companies sprouted out of Texas and they went overseas and they took their big black book with them telling them how to do things and they left a copy for the government? In some cases, yeah. What are other cases? Any idea? What about the province of Alberta, or as we like to call it, North Texas? You guys ever been to Alberta? They have some of the most incredible testing requirements on Earth. You actually have to run a pressure buildup test on your well every 4 years. You know who invented the legislation or who wrote the legislation? The vendors and the engineers did. I mean, they're Canadians, so we assume they're Boy Scouts and they had only good intentions. But the reality is, it's a pretty good idea to test all your wells periodically. Can you name a company that tests every well every year? It ought to be like that. Saudi Aramco. Test every well every year. And I'm sure there are other national oil companies in the Middle East that do the same. However, this creates interesting contradictions. Because they test wells in Alberta, they don't necessarily have very good production data. Because they figure, like one of the doctors, every 4 years, you're going to get a complete checkup. So what you do in between now and then doesn't matter. That's not a good idea. But the other thing is, in Alberta, everything, generally speaking, is public data. If you really want to entertain yourself this afternoon, go look at North Dakota, because virtually everything in North Dakota is public data. You can pull it all off of their website. There are other state websites that are equally fairly easy to use, but Alberta is one. Many countries have all of their data as public data, which is kind of interesting. I guess they figure there's no competitive advantage, so they may as well put it out there. Australia, New Zealand, countries like that seem to have quite a bit. This is the derivation of the equation on the previous page. And I won't bore you by making you go through every step, but this is the steady state form of Darcy's law evaluated for a constant viscosity Z factor, and you get exactly the equation you saw on the previous page. I'm not saying that this is the right way to derive this, because of course we assume pseudo-steady state or transient flow on the previous, but the relationship is so simple, I told you before, it was empirical, that it can actually be derived from fundamental principles. Not to suggest we should be using the steady state equation, but I'm just pointing out that we can use the steady state equation, and here's how we would derive that expression on the previous page. So, somebody came up with an empirical relationship. It can be derived directly for steady state flow. It can be derived sort of for transient flow. It can definitely be derived for pseudo-steady state in a variety of different fashions. So the real answer to the question is, so what? Well, I'm just trying to point out that from very simplistic beginnings is a start of an understanding of pressure transient analysis. Now, looking at this particular slide, what's missing? If you tell me what's missing, I'll let you go. If you make me stay, I'll take it out. I'll torture you in the next 15 minutes. I'll torment your soul. You'll fall asleep tonight, you'll see this equation, and you'll recognize what's missing. You got enough? What does this describe? What variable's missing? Sorry? It's 146. Time. Did I give you enough hints? Is that you, Mr. Pilot? No? Oh, not the pilot. Time. Is time implicit in average reservoir pressure? Sort of. We can say it's sitting in there. But this does not describe pressure and rate behavior as a function of time. It describes it as relative to each other. So how would you make a prediction with this? There are ways of doing it, but what would you have to do? You'd have to couple a material balance equation with this. You'd have to make a rate prediction. You'd have to convert that to a volume. You'd have to then calculate the material balance, average reservoir pressure, then make another prediction, and so on. It'd be like a simplified predictor-corrector type method. You can make a projection. You could do that. So this only gives us a fundamental understanding of the behavior of these functions relative to each other. This is the last slide we'll go over. I know we didn't get nearly as far as we wanted, but that's all right. We got 6 lectures. I'll talk real fast. This is taken out of a book written by a really good friend of mine. This is the Energy Resources and Conservation Board Manual from 1975. It was written by Louis McCarr. who is presently head of Propagate. It's a very nice diagram explaining flow regimes. It's a very nice diagram explaining flow after flow or 4-point test. 1, 2, 3, 4. This goes line, line, line. Line, increase. And then we take these data and we plot them on this particular plot, and we can make that projection. I'm tired, man. You've been here 4 hours? Just 2? It just seems like 4. You weren't in here before. So why did we use the 1975 version of the Energy Resources and Conservation Board manual? It's a trick question. It's also irrelevant. Anybody? It's because that was the last version before they went metric. So, if you look at this particular diagram, it explains the concept of a flow after flow test. I want you to get through your head that the reason these old ways worked was because they were simple, they were straightforward. Would you consider using a flow after flow test now? Yes, no, maybe? I would. If a company would allow me to do it, I would do exactly what's on point B every time. I would gently start the rate, I'd ramp it up. I might have a Q5, which would be an extended rate, and then I'd shut in the well for a long time. Why? Why don't you start the rate high and go low? How many of you drove your own car here today? So when you get in your car, do you turn it on and step on the accelerator and push it up to 7,000 RPMs? Why not? Sorry? Why? It's not good for the car. So why didn't we start this at 50 million cubic feet a day or 50,000 barrels a day and walk it down? It's not going to be good for the reservoir. So you always want to start low and work your way up. See if you start having any problems. What kind of problems would you have? Well, you could have sand, you could have equipment cutting out, that sort of thing. Just think about these simple things. Don't get in a hurry. It'd be nice to have an extended rate other than 0. In this diagram, the extended rate is 0. Let's see on my finger. But it'd be nice to have an extended rate. Again, the biggest problem is it does not relate rate, time, and pressure. It is a mechanism to compare multiple steps. Now, that's not really true. And I'll tell you why it's not really true, and I'll use up another couple of minutes. But the reason, and this is weird, it's like an old Pong game or something. Let's see if I can convince this thing to clear itself. All right. You have time here. Okay, the rate might jitter around a little bit. And of course, 0 is 0. The pressures are pretty much going to behave as presented here. If you have measurements continuously, did you guys talk about this in 648? If we have all of this data continuously, what can we do? We can use sapphire or topaz or both to analyze it, Sapphire is kind of like a laser scalpel. Topaz is kind of like a chainsaw, you know. But it's all right, we have both. But here, what we were talking about is only looking at these step rates and only looking at the pressures here, 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 and of course the initial one. So we're only really using 4 pieces of information there. But in modern sense, we've got everything measured, so we can capture all of this in a modern well test analysis, pressure transient test analysis package, as well as production. All right, we'll see you on Thursday at noon. I will post all of this either later this afternoon or this evening. Excuse me. Again, as for assignments, I'll think of something. There's too many of you to. I'll think of something. I'll sit down and I'll think about what's best for you and what's going to keep me from going insane, and that's what I'll do. So I'll think of something. Sure. I got to run with a call too. Go ahead. No, you still got that. Realize I'm going to be talking one. Go ahead. Okay. Remind me of this when we talk about the pressure distributions in the reservoir. If you want to read ahead, I think it's already canceled it out. But we're going to derive the drawdown, and you'll see how the pressure propagates through the reservoir. And then there's also a buildup version of this. And you're right that there is a continued equilibrium. But for the most part, it's not going to do what you think it's going to do. Schlumberger made a business out of something called an impulse test. And the impulse test, the principle behind it is they produced for a little while and they shut in for a long while. And this came actually from the work by guys like Carson and Kelvin and those guys, where they showed for perfect systems, you know, you could do these kinds of things where you could have an impulse solution and you could see the pressure decay in the system and all that. But the reality is, in a reservoir, you're not going